Yeah, yeah, I have a small doubt. So is it okay if I leave a timer on the side just to keep track of time from my end? Okay, thank you.
All right, you may start when you're ready.
In a world where billions of data points emerge every second, decisions hinge on thousands of comparisons. But how do we ensure that these results are valid? Let MultiDST handle it. MultiDST, multiple testing made easy.
Good morning, dear judges and everyone. We are from the University of Colombo, working in collaboration with the Tokyo Metropolitan Institute of Medical Sciences to bring out our product, MultiDST, multiple testing made easy. Let me first share with you an infamous tweet that many of my friends shared and reshared and retweeted. This gentleman here claims that whenever the p-value or the result that we get from a statistical test is less than 0.05, we can simply reject it. But is this always the case? Let me take you through a scientific study. A group wanted to know an age-old question: do jelly beans cause acne? So what did they do? They tested in two groups and checked if giving jelly beans caused acne. First, it might be not significant. Then someone would claim no, only a specific color of jelly beans would cause acne. Then you would give colors and then test it accordingly. This way, you'd be doing tests for red, orange, yellow until you get a positive result with green, and then you can say green jelly beans cause acne. But is this always true? No, this is a scenario called p-hacking, and this is a big issue in this era when we are working with billions and billions of data. So this is the problem of multiple comparisons, where when we do multiple tests again and again, the type 1 error or the false positives will go up. So correction procedures are needed. So even though our experiment procedure and the data collection is on point, if we don't do this correction at the very end, results can be detrimental. One scenario that this is happening is in medical sciences in differential gene expression, gene expression analysis, where we have to compare different gene locations of human beings to see if a disease is occurred. So the human being is known to have 20 to 25,000 genomes. So a p-value of 0.05 means we have 5 false positives in 100. So imagine in 20,000, just in 10,000 we'll be having 500 false positives. These human lives, we can't afford to have such errors. So correction procedures are needed. So with this in mind, we thought of going ahead with this and try to solve this problem. But this just doesn't stop at medical data. It goes into economics, where we are doing comparisons of cohorts and scenarios to find out which one would be onerous and which one would be profitable. Actuarial sciences, computer, where we are doing multiple comparisons. So the use cases are beyond one point. And this has been studied for almost 100 years. But up to date, there is no single framework that fuses everything together and gives the user a way to find out this is the best method under this scenario. So although there are methods scattered around the literature and in the world, we don't have a single method or a framework that uses all of this in one place. So this is our problem, and we are solving it in two different ways. So first, we went out with our research and methodology to go through a thorough literature survey to find out different methods that would perform well. So using those use cases in our mind, we found out that there are ways of like controlling two types of errors: family-wise error rate and false discovery rate. And under these, through the literature, we shortlisted 6 methods that have been found to be useful in literature, and then we went on into a comparative simulation study to see how these methods would perform. Using parallel processing, we fastened the process of simulation testing and tested under 2 scenarios of t-tests under multiple iterations to come to a good conclusion. So after doing the conclusion under both the t-test scenarios, we found out that when we are thinking of power or the true positive rate, we are having the FDR control methods perform better. But when we are controlling the precision, in terms of precision, the FWR control methods would perform better. This shows that we can't simply rely on one method. We need a fusion of all the methods. So that is the reason we went on with our study even further. And there was another gap that we identified in terms of locating. So from this novel plot that we are introducing as part of our study, we can take a look at this graph, the significant index plot, which we call it. From top to bottom, a line would mean that it has been rejected or signaled by all 6 methods, which means a scientist can have a good idea, okay, this might be a useful test case. So that, or a significant test case because it's rejected by all the methods. This plot can be zoomed in until you can see it on an individual level. And then we went into another simulation study under 4 different settings. I have shown one setting here where we can find out which method would perform best given the p-values, the data sets that we have. So as I said, we can also find out which methods are detected by all 6 methods, giving them a higher weight. That way the false negatives would be pushed that way. So using these procedures, we came up with a weighted hybrid framework where we can tell a user a single way to apply these methods of correction. This was all that there was at the beginning, and that too only one method at a time. Now we are introducing a visualization process and then a hybrid methodology where you can retest and take out the values and then take a good look at it as well. And then this framework we are introducing in a way to demystify this black box that's going around in multiple testing. So we present 2 solutions, as I said before, one for programmers in terms of a Python library which can be installed just using pip install MultiDST, and another using a MultiDST user-friendly website which is also available under www.multidst.site. So using this, we can use it on a data set. So one data set, the first one that we used was genomic data set, where we have studied under 2 different p-value creation settings, and then under these 2 scenarios, we even performed independence hypothesis weighting, where the gene title known scenarios would have a higher weight compared to those without. So using this, we found out which method would perform best in this scenario. And the use cases don't stop here. We can also have use cases in finance and insurance. In finance, we would like to know which cohorts would be most profitable. In terms of an insurance company data that we used in this case, we can find out at which fund types or at which fund type levels are policyholders going to stay until the very end, which means they have gone up until maturity, or which policy case they will stop payment midway, which means they have gone into a surrender. So which types of portfolios would go into this scenario more. So under each of these portfolios, we can get the p-values and do the t-testing just by a single click. So that is the specialty of our website. It's not just common to one framework, it's common to all the frameworks, all the domains as well. So this is our user-friendly website input as well. So why choose MultiDST? Because we are demystifying this black box, and we can even use it with large data sets. And then our competitors are the United States National Institute of Health, where we even got the data sets that we initially needed in terms of p-values. But they only have 2 methods, and they don't have this framework built in. We have this framework, and we have 6 methods, which gives that bit more of credibility to the user. So we tested, and we got the approval from many of our experts from the China in terms of genomics, and from the insurance company that I got the data by, and then from Japan, from the United States, and from our own biostatistics lecturer at University of Colombo as well. So we have got the approval, and then that this framework is very useful in the scenarios. So this can be used in biomedical engineering, in any field involving multiple testing, and in financial analysis, embedded value, where we can find out the financial statement and come to a good conclusion in a very easy manner. So the research institutes and universities all around can use, and even a higher end CEO level person can go to the website, simply go to the website, give the p-values, and then see which cohorts are most useful. So this is what we offer. We offer multiple testing in one click, powerful visualizations, the high weighting technique, and then the common indices where we can give the weights in the way we like. So we have also applied for copyrights through the university, and then we are in the process of going through that. And we have also research publications. The abstract is already accepted for a conference talk at the International Statistics Conference happening in Colombo later this December. And the full paper publication is in review stage. We have submitted to the Royal Statistical Society in the United Kingdom. So we are giving MultiDST as a business solution with the vision of empowering the researchers, and with the mission of making Asia Pacific region known in terms of this framework, and then that we are building useful frameworks and giving the power to the user, to the scientific community, to come into more sound, more accurate conclusions with less blinded results. So these are the frameworks that we used, and we would like to take you through a demo video of our website right now. stop? Okay,
We can go on. We can go on.
I can go on.
Alex, I think you are ready
Thank
to
you.
ask.
You want me to close